The light turns green. Your foot moves from the brake to the accelerator, pressing down with intention. The car, which was just sitting still and humming quietly, comes to life. The engine's note deepens, and you feel a gentle but firm force pushing you back into your seat as the world outside begins to blur slightly. It's a feeling every driver knows intimately, the simple cause and effect of pressing the gas to go faster. But this seemingly straightforward action triggers an incredibly complex and lightning-fast sequence of events deep within the heart of your vehicle. It's a mechanical and digital ballet, choreographed to perfection, all happening in the blink of an eye. This entire process is about delivering your desire for more speed to the engine in a language it can understand. This command begins not with a roar, but with a whisper of electronic data. In most modern cars, the accelerator pedal isn't physically connected to the engine with a steel cable anymore. Instead, it's a sophisticated sensor. When you press down, you are essentially turning a digital knob. A small electronic module measures the exact angle and how quickly you pressed it, converting movement into an electrical signal. This is the first message in a chain carrying a vital request: more power, now. Once the ECU receives the signal from your foot, its first major executive order is sent to the throttle body. The throttle body is essentially the gatekeeper for the engine's air supply. It's a metal tube located between the air filter and the engine's intake manifold. Inside is a flat, circular valve called a butterfly valve. At idle, the plate is almost closed, letting just enough air through to keep the engine running. When commanded, an electric motor rotates the plate, drive-by-wire control. It opens to a precise angle that corresponds to your pedal, perhaps 25 or 30% for a light press. That angle allows a measured volume of air to rush into the engine. This control is incredibly precise, giving modern cars their smooth, predictable response. The ECU can even modify your input for efficiency, safety, and ride smoothness. On slippery roads, it may limit throttle opening to prevent wheel spin. It can smooth a jerky pedal input for a calmer ride. Opening the throttle is the first physical step to more power by letting more air in, one of two key ingredients for combustion. Without enough air, extra fuel only chokes the engine. Every horsepower begins as carefully metered air past this valve. Your simple press initiates that airflow, and the power that follows. With the throttle plate now open, the engine can finally take a deep breath. Air passes through the filter to remove dust and debris. Then the descending pistons create a vacuum, like massive syringes drawing in air. The wider the throttle, the less restriction, and the easier cylinders fill with fresh air. Air volume largely sets the engine's potential power. The ECU must know how much air is entering. The mass airflow (MAF) sensor, after the filter and before the throttle, measures it. A heated element is cooled by airflow. The current needed to keep it hot tells the ECU the air mass. This data is vital to calculate matching fuel. Air continues through the throttle into the intake manifold, which distributes it as evenly as possible to each cylinder. Runner length and diameter, and sometimes variable flaps, optimize low-end torque or high-end horsepower. More oxygen molecules let you burn more fuel for a stronger, controlled explosion. Colder, denser air has more oxygen. Cars feel peppier on cool mornings. High altitude reduces oxygen and power. From the air filter to the intake valves, the goal is simple: help the engine breathe freely and efficiently. Once the ECU knows how much air is entering, it calculates the perfect amount of fuel to mix with it. The ideal for gasoline is about 14.7 parts air to 1 part fuel by mass, stoichiometric. It enables complete burn for power while minimizing unburnt hydrocarbons. ECU maps provide base fuel for given airflow and engine speed. When airflow surges, the ECU consults its maps immediately, like a chef following a precise recipe. Cold starts need a richer mix because gasoline vaporizes poorly in a cold cylinder. At full throttle, the ECU enriches around 12.5 to 1 to help cool the chamber and prevent knock. Under light load, some engines can run a bit leaner to maximize fuel economy. Oxygen sensors read exhaust to tell the ECU if the last combustion was too rich or too lean. The ECU corrects in real time. Closed-loop control keeps the ratio optimized for power, efficiency, and emissions. It balances your need for power, your wallet, and the environment hundreds of times per second, and it never stops adjusting as your right foot and the road demand. The brain of the operation, the engine control unit, the ECU, a small but powerful computer, tirelessly managing torrents of information and decisions every second. Pressing the accelerator submits a request. The ECU interprets and orchestrates the response. It listens to the mass airflow sensor, the crankshaft position sensor, the throttle position sensor, the coolant temperature sensor, the NOx sensor, and the oxygen sensors. Each sensor is a piece of the puzzle, giving a real-time picture of engine health. The ECU controls fuel injection amount and spark timing using complex maps. It calculates injector open time in milliseconds. Simultaneously, it picks the exact moment to fire the spark plug. Too early risks knock, too late wastes power. The ECU balances continuously. It also manages variable valve timing, idle speed, coordinates with the transmission, and oversees emission systems. As master conductor, its flawless timing is what you feel as smooth, responsive power. With calculations made, the ECU commands the fuel injectors and the ignition system. Injectors are tiny electronically controlled nozzles, one per cylinder, metering precise fuel. A pintle valve snaps open and releases a fine atomized mist for thorough mixing. Some spray into the intake port. Direct injection sprays right into the cylinder. Pulse width, how long the injector stays open, controls how much fuel is delivered. Longer pulses enrich for power. Shorter pulses lean out for economy. After air and fuel mix and compress, a spark ignites combustion. The ECU picks the exact moment to send high voltage to the correct plug, ideally just before top dead center, allowing the flame front to build peak pressure on the power stroke. At higher RPM, it advances timing because there's less time to burn, guided by the crankshaft position sensor. If knock is detected, timing is retarded instantly to protect the engine. Dynamic fuel and spark control, perfectly synchronized, is how chemical energy becomes mechanical force. When you stomp the pedal to merge, the sensor flags wide open throttle and the ECU prioritizes power. It opens the throttle wide, enriches the mixture and advances timing for peak torque. It coordinates a downshift so the engine lands in its power band. You feel that surge as the car leaps forward. A slow, light press is read as low urgency, smoothness and economy take priority. The throttle opens slightly, fuel increases a touch, and AFR stays near 14.7 to 1. The trans holds a tall gear. Low RPM torque gently builds speed. You get a calm nudge forward, minimal sound change, and low fuel consumption. This duality, thrilling or tranquil, comes from how the ECU interprets your foot. One car, many characters. Enabled by smart engine management, rate and amount of pedal movement shape throttle, fueling, timing, and shifting, moment by moment. A perfectly timed spark ignites the compressed air-fuel mixture, a controlled explosion. Expanding gases create pressure that drives the piston down. The power stroke, intake, compression, power, exhaust, everything builds to that powerful push. The piston's up-down motion becomes crankshaft rotation. Multiple cylinders fire in sequence, smoothing rotation. That rotating force is torque. Torque flows through the transmission, a gearbox and torque multiplier. Low gear multiplies torque to overcome inertia from a stop. Higher gears reduce multiplication so the engine runs efficiently as road speed rises. Power exits the transmission via the drive shaft to the differential. The differential turns rotation 90 degrees to the wheels and lets left and right rotate at different speeds while cornering. Axles deliver torque to the wheels. Grip translates torque into motion. Your request becomes forward movement. In the end, pressing the accelerator is like starting a domino rally of incredible speed and precision. Pedal to ECU, throttle and air, fuel injectors, spark, piston, and finally the wheels. Sensors are messengers. The ECU is the decision maker. Mechanical parts are the actors. The system can deliver a thrilling burst or a gentle, efficient cruise, depending on your input. It's a century of engineering refinement culminating in a smooth, reliable, responsive drive. Dirty air filter? The engine starves for air. Clogged injector? The air-fuel ratio is disrupted. Faulty sensor? The ECU makes decisions on bad data. Each part relies on the others. Keep them healthy for proper response. Routine maintenance preserves performance and efficiency. One simple tip: practice smooth driving. Occasional bursts are fine, but constant abrupt pedal and brake inputs stress the drivetrain. Smooth inputs are kinder to the engine, transmission, and brakes.